Good afternoon, everybody. I'm glad to be here. It's my first time at Modelica User Conference. I'm here to present you the work that we made in collaboration with Claytex to develop a race car braking system thermal model for a real-time use in a driving simulator. So this is the agenda of my presentation. I will start with an introduction of my company, Dallara, and Claytex and the partnership with Claytex. Then I will move to the core of the presentation, so explaining you the simulation model at the result that it brought. And at the end, it will be time to draw some conclusion and analyze the further developments. To explain, to illustrate you Dallara, I start with a picture where we have our founder, Mr. Giampaolo Dallara, and our CEO, Andrea Pontremoli, with our first road car, that is the Dallara Stradale. And yeah, here there is a challenging and important statement that is our mission. So our aim is to design and produce the fastest and safest car in the world. The fact that also our founder based the company in his hometown and gave his surname create a special connection with people and territory, well represented by the fact that by our vision. So some numbers now, yeah, this is for 2024 year. Fortunately, 2025 has been our best year. Now we are approximately 1,000 employees with an annual turnover of 250 millions. And yeah, we export approximately more than 80%, basically divided in three main business units. We have got the racing business unit. Here are some of our products. We have got the IndyCar. We produce all the cars for the IndyCar series. And then our latest work is all the LMDH program, where here is the Cadillac and also BMW. We work with them. Then we have got the automotive business unit. Here, of course, our Dallara Stradale. And then an important project that we follow, so the Bugatti Bolide. And then, of course, we have also a new business unit. We started it some years ago and is more focused on the aerospace. We have got 5 facilities here, and yeah, 4 of them are in close to Parma. We have got Dallara Automobili, that is our headquarters, then Fabbrica Dallara and Dallara Academy, based in Varano. In Collecchio, 15 kilometers from Varano, there is our composite production facilities, and then one in the United States to better follow all the American projects as NASCAR and IndyCar. So I work as a vehicle system engineer. We are mainly focused on 3 activities, so calculation and simulation, testing, and then, of course, research activity. For the calculation part, we mainly perform 1D simulation, holistic simulation, to define the layout of cooling system for each type of cars. Then we have additional work, HVAC system sizing. Of course, the reason that I'm here, so 1D brake cooling analysis, and then some 3D analysis using meshless software. Here, for example, there is a tank sloshing analysis. And in the latest part, we also started to make some driveline torsional vibration analysis. For the testing part in Dallara, we have our cooling test bench, so we can perform for external customers measurements, performance measurement on water and oil radiator, and then, of course, we make some track support, track validation. And for the latest part, the academic, we have attend some lessons at the Muner, that is the Motor Vehicle University of Emilia-Romagna, and then we also write some paper and attend conferences. So to explain you the partnership, this activity, as I mentioned, is a cooperation between Dallara, which is responsible for the case study, and Claytex, who developed the libraries used to build up the simulation model. In fact, in Dallara, we use the vehicle system modeling and analysis simulation suite, and yeah, this model may run offline or directly in the Dallara driving simulator. Here there is a picture of it that is in our headquarters. And yeah, moving now to the core of the presentation, our target is to simulate with an holistic approach all the powertrain fluids temperature, the brake temperature, and the vehicle dynamics to optimize the overall vehicle performance. That is our main target. So this activity, the starting point was the Dallara full vehicle model, where we have our chassis and powertrain that are discretized. Here, the starting point. 2 years ago, always at Modelica conference, we integrated a car cooling system model inside it. So as you can see, we took as output from the vehicle model engine speed, vehicle speed, and heat rejection, and that allow us to evaluate the temperature and the temperature for the oil and for the coolant, and this, of course, this value will affect the performance according to the ICE, the rating strategies given by the supplier. In this activity, in this step, we also added another part, so the braking system thermal model. Again, we took as output the wheel speed, the vehicle speed, and the brake power, and evaluate the disc and the caliper temperature. This, of course, will affect again the overall performance, because an increase disc temperature will decrease the friction coefficient, causing a decrease of braking power. So now moving to the discretized component, in the model we discretize the disc divided in inboard, outboard, and main part, the core part. Again, the caliper, same structure as before, so inboard, outboard, and core. The brake bell and the rim. The rim is again divided in two parts, so the one that takes all the rim, the spokes, and the another one that takes the part close to the tire. Looking now at the main input parameters, of course, a fundamental one is the heat transfer coefficient map. This is something that we evaluate from our 3D CFD analysis department. And so this is fundamental to consider the convection and radiation with the ambient air. It's a map function of the component heat rejection and the vehicle speed. Then again, some physical properties, density, emissivity, conductivity, specificity of each material. And another important and crucial part is the brake friction coefficient map. This is a function of temperature and brake pressure, and is given by the brake supplier. This is a map, and as you can see, by increasing the brake pressure and the temperature, the friction coefficient will decrease drastically, causing a bad braking performance. And yeah, of course, this model may run offline or in the driving simulator. So if you run offline, you need, for example, some input data as vehicle speed, wheel speed, brake pressure, and so on. Now, analyzing how the model is built and the thermal discretization, we start by the evaluation of the brake power, that is the overall system heat rejection. This is the equation that we use, is the standard equation that you can find in literature. Then starting from this, our model is divided into two submodels. One of them is used to evaluate the temperature of the disc and the neighbor components, and another one for the disc caliper. So we start assigning 93% of the overall brake power, the heat rejection, to the disc outboard, inboard, and outboard surface, equally distributed. This is something. This number is empirical. We look at some recent paper, and overall this is a value that is good. And also we tested on, we make some simulation on several type of Dallara vehicles, and yeah, overall this value felt always in this range, so it's a good approximation. Then again, it starts a sort of thermodynamic chain, because the heat from the inboard and outboard part will go inside in the core, and then from the core to the brake bell and then the rim. So you have to consider that all this conduction will happen, and it has to be evaluated taking into account the reference length and reference area of the component, the interface between them. And after this, we can analyze all the thermodynamic flux. Of course, each of these components dissipate heat through convection, and so we have to add again this component, this part that is evaluated with the friction, with the heat transfer coefficient evaluated by the 3D analysis. So the remaining 7% of this heat rejection is assigned to the caliper core, and then again it's the same situation. From the caliper core we have got a conduction to the inboard and outboard part, and then a dissipation through convection. Thanks to this structure, we can evaluate each component heat rejection. And after this, we can proceed to the temperature evaluation. So this is something very easy, because we have just to apply the first principle of thermodynamics. I mean, it's an energy balance. We have got an input heat rejection coming from a neighbor component. Then we have got a heat dissipation through convection and conduction. And at the end, this with balance will allow to evaluate the instantaneous flux, and then through using an integrator block we can evaluate each component temperature. Here there is the equation taking into account the thermal capacity and the heat flux. So, of course, now moving to the more interesting part, the validation represents the crucial moment to assess the correctness of the model. And we started taking a braking system architecture of an existing vehicle, and we compare the measured data to the track. And here is the result for the disc and the calipers. For the disc, we had an average difference between measured and simulated of about 12 Celsius degree, with a root mean square of 15. These consider the high range values, because we start from 400 Celsius degree arriving to 800, represent from our point of view a good error that allow us to better and to size in a good way the braking system thermal area. This is for the caliper data. Instead, here we have an average difference between the measured and simulated of 3.3 and a root mean square of 3.9. Again, this was an offline validation, so we give imposed vehicle speed and wheel speed and brake pressure, taken directly to the car sensor. But of course, we implemented the simulation model also in the Dallara driving simulator, where a driver performed a series of laps at maximum performance. Here is this acquisition is from an hypercar with more than 1,000 horsepower, and yeah, analyzing this, we can see that approximately the peak temperature for the disc stabilizes between 900 and 1000 Celsius degree. There is a little imbalance between the front left and the front right temperature, probably due to the ABS system. In the paper there is also a picture where you can see the different brake pressure. And yeah, one interesting part turned out to be the friction coefficient values, because as I mentioned before, it is discretized as a map function of pressure and temperature. And as you can see, increased temperature when we have at the hardest braking zone leads to an overall friction coefficient degradation, which is reduced by more than 20% in the heaviest braking. Then, of course, from 20% from the nominal value and the target value that the brake supplier give us. Of course, it's fundamental, the temperature, in this case, is so-called end of straight temperature, so before the braking zone. The same exercise was also done for the rear brakes, and here, of course, the temperature is lower, approximately 350 Celsius degree lower, and in fact, it stabilizes between 600 and 700 Celsius degree. And in this case, we have a completely different trend in the friction coefficient, because less temperature and also less pressure in the rear axle, and so approximately we have a value that is more approximately constant, and just 2 turns lead a reduction of about 10% from the nominal value. So now I'm at the end of my presentation. Analyzing the conclusion, we can see that the simulation model has been correctly validated with track data, and it's currently used at Dallara to cite the braking system and analyze the vehicle performance. The simulation, this tool can be also useful and is very useful in preparing a race weekend, because we can analyze in simulation different type of air duct size. Of course, the air duct size will affect the heat transfer coefficient map of the component. So thanks to this, our 3D CFD department can prepare the different maps with different heat transfer coefficient, and then we will test offline, analyzing which is the best condition, the best trade-off between aerodynamic performance and cooling effect. This in the duty cycle, also analyzed in the driving simulator, was track lap at maximum performance, but of course we can analyze different driving cycle. For example, crucial nowadays is the out lap before a qualifying lap, or during safety car, under safety car, to hit the brakes before the racing start. And yeah, also one key aspect of the model is turns to be out the friction coefficient sensitivity, because now it's possible to evaluate all the impact on the lap time performance. Now, just the last slide, the further developments that we want to add to this simulation model. The actual status is that the thermal discretization, as I mentioned before, stops at the rim. And this temperature is used as a border condition for a tire model, for a tire thermal model. The next step that you want to implement is to predict the thermal conduction and convection from the rim to the tire, and integrate inside the vehicle model a tire thermal model. So thanks to this, we will able to analyze the tire temperature, having as input, of course, from our driving simulator, the tire acting force and torques, having again the rim conduction and convection. We will be able to predict the tire temperature, and again, thanks to this, we are able to analyze a friction coefficient, the friction coefficient between the tire and the road. This, of course, will expand again our analysis, taking also into account the longitudinal and the lateral grip generated by the car. So now I'm at the end of the presentation, and yeah, if you have got some question, I'm here. Thank you so much.